Welcome, everyone. Today we're doing a deep dive into, well, a rather curious entry in the online encyclopedia of integer sequences. It's T000200R.
Ah, yes, the one titled Number of Bicentered Hydrocarbons with N Atoms.
Exactly. And for, number theory students exploring the OEIS, seeing hydrocarbons might seem, a bit out of left field. Organic chemistry, right?
It really does bridge disciplines, doesn't it?
Yeah.
The immediate question is, why are we counting molecules in a math database?
That's our mission today. Figure out what these bicentered hydrocarbons are, and importantly, why counting them generates this specific integer sequence. We've got some chemistry texts, online explainers, quite a range.
And the core idea, I think, is to understand the structure. If we get the structure of these bicyclic compounds, the counting part, well, that should start to make mathematical sense.
Okay, so let's start there. Bicyclic compounds, what are they, fundamentally?
Fundamentally, they're organic molecules with two rings. Two loops of atoms, if you will.
And these rings have to share at least one atom, right? That's the key.
Precisely. They have to be connected, not just floating near each other. And how they connect gives us different types.
Right. Our sources mention three main ways. There's spirocyclic.
Yes, spiro. That's where the two rings share just a single atom, like two rings joined at one point.
Okay, one shared atom. Then there's fused.
Fused bicyclic compounds. Here, the rings share two atoms, and crucially, those two atoms are directly bonded to each other. They share an edge, you could say.
Share an edge, got it? And the third type?
That's bridged. They also share two atoms, but these shared atoms are not directly bonded to each other. There's a bridge of one or more atoms connecting them across the structure.
Okay, spiro, fused, bridged. Now, the sequence name, A000200, uses bicentered. That sounds specific.
It does, and looking at the context, bicentered almost certainly refers to systems where two centers, two atoms are shared between the rings.
So that would mean fused and bridged types. Both share two atoms.
That seems the most logical interpretation. Spiro compounds, sharing only one atom, probably aren't what A000200 is counting under the bicentered label. It focuses the problem on those two shared atom structures.
Right, that makes sense. And these shared atoms, they're typically carbon atoms in hydrocarbons, aren't they?
Yes, we're dealing with hydrocarbons, so compounds of only carbon and hydrogen. The backbone, the rings, are made of carbon. The centers being shared would be carbon atoms.
And these shared carbons in fused and bridged systems, they have a special name, don't they? Bridgehead carbons.
That's right, bridgehead carbons. They are the connection points. And how many other carbons form the paths or bridges between these bridgeheads determines the specific molecule.
And that relates to the naming convention, the nomenclature.
Exactly. For these bicentered, likely fused and bridged systems, you see names like bicyclo, then brackets.
Like bicyclo 2.2.1 heptane. I saw that example quite a bit.
We're classic. The bicyclo tells you it's fused or bridged. The numbers in brackets 2.2.1 tell you the lengths of the bridges connecting the two bridgehead carbons.
So two carbons in the first bridge, two in the second, and one in the third, and they list them largest to smallest.
Usually descending order, yes. And the heptane part. That tells you the total number of carbon atoms in the entire molecule. Heptane means 7.
Okay, so the name itself encodes the structure. 2 bridgeheads plus 2 plus 2 plus 1 bridge carbons. That's 5. Wait, heptane is 7? Where are the other two?
Ah, good catch. The bridgehead carbons themselves count towards the total. So the 2 bridgeheads plus the 5 bridge carbons make 7 total.
I see. So the numbers are just the carbons between the bridgeheads.
Correct. And that systematic naming reflects that we can, in principle, systematically build and therefore count these structures.
Which brings us back to the sequence. A000200 counts the number of bicentered hydrocarbons with N atoms. So N is the total number of carbons.
It seems overwhelmingly likely that N refers to the total number of carbon atoms, yes. So the sequence lists for N1, Ne2, Ender3, and so on, how many distinct bicyclo-alkane structures, fused or bridged, are possible with exactly N carbons.
And we need to consider isomers here, right? Same number of carbons, but different arrangements.
Absolutely crucial. For a given N, you might be able to connect the carbons to form different bicyclic skeletons, different bridge lengths, for example, while keeping the total N constant. A000200 is likely counting these distinct structural isomers.
So for any 7, bicyclo 2.2.1 heptane is one structure. But maybe there's another way to arrange 7 carbons into a bicentered hydrocarbon, like bicyclo 3.1.1 heptane.
Potentially, yes. You have 2 bridgeheads, then 3 plus 1 plus 1 plus 5 bridge carbons, total 7. That's a different isomer. The sequence value for NS7 would count all such valid possibilities.
Okay, this is starting to click. It's a combinatorial problem rooted in chemical structure rules. The valency of carbon forming 4 bonds and the rules for forming two rings sharing two atoms. These are the constraints.
Exactly. It's combinatorics with chemical rules. How many distinct graphs, essentially, can you draw following these rules, given any vertices labeled carbon?
And this is where it connects clearly to mathematics and number theory. Counting problems, enumeration under constraints. That's familiar territory.
It is. It shows how abstract mathematical concepts find concrete application, or perhaps even inspiration, in describing the physical world. The sequence A000200 is the numerical result of applying these chemical construction rules.
It's interesting, too, that these bicyclic structures aren't just theoretical curiosities. We see them in nature, right?
Oh, definitely. And many natural products like terpenoids, think camphor, or pine from pine trees, have bicyclic skeletons. They are common building blocks in organic chemistry.
So understanding how to count the basic frameworks might even help in understanding the diversity of more complex molecules built upon them.
It provides a foundation, certainly. The principles of constructing and counting these simpler systems are relevant to more complex polycyclic structures, too.
Okay, let's try to summarize then. We started with OEIS A000200 bicentered hydrocarbons. We figured bicentered most likely means bicyclic compounds, where two carbon atoms are shared between the rings, so fused or bridged systems.
Right, excluding the spiro type, which shares only one atom.
And the sequence itself, A000200, seems to be counting the number of distinct structural isomers of these specific bicentered hydrocarbons that have exactly daron carbon atoms in total.
That appears to be the core of it. It's an enumeration problem arising directly from the rules of organic structure.
So for the number theory students listening, this sequence, despite its chemical name, is really about combinatorics. It's about counting arrangements under specific rules.
Precisely. And it's a great reminder that interesting mathematical problems, interesting sequences, can pop up in unexpected places. Chemistry, biology, physics, they all have structures and rules that can lead to enumeration questions.
So the invitation really is for listeners to check out A000200 on the OEIS website itself. See the numbers, look for formulas, comments, maybe even links to graph theory concepts.
Definitely. Seeing the actual sequence values, the recurrence relations, if any exist, the references, that's where the deeper mathematical connections might become apparent.
It really makes you wonder, doesn't it? If counting these carbon skeletons gives us this sequence, what other natural systems, with their own rules, could be described by integer sequences we haven't even discovered yet?
That's a fascinating thought. The universe is structured by rules, from particle physics to cosmology. How many of those structures, governed by quantifiable rules, could be mapped onto the landscape of integer sequences? It suggests mathematics is not just a tool to describe reality, but perhaps a reflection of its fundamental nature. Exploring A000200 might just spark some new perspectives on that very idea.